Ali Kujuri. I'm an adjunct professor in the Department of Engineering Science, and then also one of the organizers of this lecture series. On behalf of our department and the School of Science and Technology, I would like to welcome you all to this lecture series. And as usual, I want also to thank Agilent Technologies for sponsoring this lecture series since the start in 2006. In fact, I was talking to David that we have had so far about like over 100 lectures, and majority of them have been from Agilent Technologies, and they have been supporting us in everything, basically, as far as all sorts of resources and so forth. Before I introduce our invited speakers, let me mention that on April the 19th, we are going to have another interesting talk titled Cloud Networking. And this will be delivered by Dr. Patrick Pfeffer, a friend of mine, who is in fact in Juniper Networks. He is in fact a senior director of strategy. In fact, he basically wants to find out what's going to happen in the near future or whatever. Our guest speaker for today are Dr. David Root and Dr. Radek Biernacki from Agilent Technologies, and the title of their talk is Circuit Emulation for Computer-Aided Design. Dr. David Root is presently Agilent Research Fellow at Agilent Technologies Measurement Research Laboratories in Santa Rosa, California. His current responsibilities include nonlinear device and behavioral modeling, large signal simulation, and nonlinear measurements for new technical capabilities and business opportunities for Agilent. Dr. Root has authored or co-authored over 100 peer-reviewed scientific publications. He was 2006-2008 IEEE Microwave Theory and Techniques Society Distinguished Microwave Lecturer, and shared the 2007 IEEE Automatic Radio Frequency Technologies Group Award. Dr. Root is a fellow of IEEE, and he holds a Bachelor of Science degree in physics and mathematics and a PhD degree in physics, all from MIT. Dr. Radek Biernacki has been with the R&D of Agilent EE Soft, electronic design automation. In fact, they will tell you about the EE Soft, I think, briefly, so that you know what it is. Basically, it is the knowledge center which provides the EDA software, and also the support and the downloading and licensing and so forth. He is responsible for a broad range of areas in simulation technology, primarily for advanced design system. Prior joining Hewlett-Packard and Agilent Technologies, he worked for both EDA industry and academia. He received his PhD degree from Warsaw University of Technology in his native Poland. He is an author or co-author of more than 100 papers. His interests and contributions have been in the areas of circuit theory, stability analysis, harmonic-based balance simulation, statistical analysis and modeling, active device modeling, optimization, and behavioral models. Dr. Biernacki is also a fellow of IEEE. Here they are, and let's welcome them.
How shall we switch to this one?
Okay.
Okay. Well, thank you, Professor Kujuri. Can you hear me well in the back? Thank you, everybody. And before I move, I will stay for a short while on the title page. The title of this talk is on computer-aided design. And this is a very broad field, and includes things like VLSI layout generation, mask generation for IC processes. Within that, we want to focus on circuit simulation, but circuit simulation also is a broad area within this computer-aided design in electronics. We had to decide what to present, and we discussed that what can we fit within 1 hour, and assuming sort of broad audience, we decided about talking about sort of the basics. So maybe some of you will be, I see quite a few power users and very knowledgeable, so some of you may be bored. Sorry for that. We will go through that and we will be talking basically about different types of analysis, DC, transient, AC, harmonic balance. We'll finish with XParameters. We decided not to talk about optimization, though originally we put that into the abstract. Let's go back some 40 years. This year is the 40th anniversary of introducing SPICE. SPICE was developed at UC Berkeley. The main developer was Lawrence Nagel, and the first version was released in 1972. And he finished his PhD thesis in 1975. And then at that time, pretty mature version SPICE 2 was released. It's interesting actually to read the first sentence of his PhD thesis. He says that the size and complexity of present, meaning then present, integrated circuits has increased to the point that computer aids are virtually indispensable. So what can we say today, 40 years later, with so much dramatic improvement and change in the speed and complexity? So anyway, throughout the decades, there was quite a few other developments. We didn't put something what we feel strongly about, 2010s, perhaps XParameters. We'll be talking about that later. In circuit design, there are many components, basic building blocks, resistors, inductors, transistors, that the designer uses to build circuits, and basically selects those components in a certain way and connects them together, and then performs computer simulation. The purpose of computer simulation is to avoid breadboarding. We don't need prototypes. We do all the work on the computer, and we want to predict the performance based on the properties of the components, and of course perhaps optimize design and etc. improve and so on. So the challenges, ever increasing challenges, are the signal complexity that comes to place, component count, nonlinearity, algorithm efficiency, etc. So it's never ending. So now we'll switch, and the next segment, David will be talking about.
Thank you, Radek. It's a privilege to be able to participate with a true expert in this area. And I've learned a lot from him over the years. I'm more a user than an expert. Let's start from the beginning. We have the simplest possible imaginable circuit. We have a battery with a fixed voltage, and we put it across a fixed resistance, and we want to solve the circuit, which means calculate the current. And we know from elementary high school physics that we simply divide the voltage in volts by the resistance in ohms, and we get the currents in amps. So we can do this in our head. It's really quite trivial. But as soon as we slightly increase the complexity of our circuit, in this case by adding a single additional component in series with that resistor, things start becoming more complicated very rapidly. In particular, if we take this component to be nonlinear, we'll call it a diode. It means the current is not just proportional to the voltage across it like a resistor is, or a constant resistor. We can come up with an equation that defines the circuit, which we'll see in a little bit more detail shortly. But the equation is nonlinear. The solution voltage, which is unknown, is inside a nonlinear function. What do? We can't do that in our heads, at least I can't. So we'll be talking about the circuit laws in more generality later, but we'll start with the example to make the point clear and concise. So we have the voltage across the resistor here, V sub R. The currents are indicated by the blue arrows through each of the elements. The component properties are given in this case by Ohm's law, V equals I times R for the resistor. And the relationship that describes the diode we'll go into in more detail, but again, the current is a nonlinear function of the voltage here across the diode. Here's where we need to invoke the circuit laws. The first of which is called Kirchhoff's voltage law, and that allows us to replace in these equations the voltage across the resistor by the difference between the battery voltage and the voltage across the diode. The second law that we'll need is Kirchhoff's current law, and that says effectively that the current through this component, I sub R, must equal the current across the diode. So those two equations, together with the properties of the components, allow us to write this equation, which is equivalent to what you saw on the previous page. That's how we generate the circuit equation. It's nonlinear again because F is not a straight line. To be specific and concrete, we'll introduce a particular model for the diode. It's cubic in the voltage across it. Now, for the experts in the audience, this is not the best model for a diode, which is not symmetric as V becomes negative V. I'm using this for computational efficiency and simplicity. So thank you for bearing with me. And then taking these particular parameter values in the model for easy computation, we can plot this function, F, of the circuit as a function of voltage. And the solution that defines the circuit is at a particular voltage V for which capital F is 0. That is the problem of circuit simulation of a nonlinear circuit. Let's see how the simulator does that. We're going to assume that somewhere between 0 and 1, which was the domain that I plotted on the graph, there is a solution. We don't know what it is, but we'll use what they're teaching more and more in schools now, guess and check. So we'll assume that we can pick V0 somewhere close to the intersection, which looks like it's about 0.7. And then we will expand the function, which is that nonlinear curve, around that value. And at the actual solution that we're trying to find, we know that the current has to be equal to 0. And we'll use the Taylor theorem, because here there's an inequality, to get an estimate of the solution. That is, to restate that, the solution of this equation will then, because this is an approximation, give us an approximate value for the solution of the nonlinear equation that we're interested in. So this simple linear equation right here can be solved explicitly, and we get our estimate of the approximate solution of the nonlinear circuit just in terms of values of the function and its derivative, that's what the prime symbol means, and the previous guess. This approximation, we hope, is closer to the actual value than our initial guess. And if not, if it's not sufficiently close, we simply stick this back into the original formula and repeat the process. So we iterate. So the theme of solving nonlinear equations, which the computer does, is an iterative set of linear solves. That's the basics. And even the most sophisticated computer algorithms largely solve equations in that way. So I'm going to show you the process using the canonical algorithm Newton-Raphson or Newton's method. that the simulators use. I'm going to use that same example. This is our function f. We're interested in finding the exact value that solves the circuit. For those of you who like algebra, you can look in the left column. We will be looking at the iterates as we start from the beginning. And for those of you who prefer graphical methods, I'll show you a nice interpretation. They're consistent. You can use whichever you prefer or both. So in this case, our initial guess at the solution that makes f 0 will take 0. That may not be the best guess, but we'll start there nevertheless. The first point in the algorithm, the first step, is to evaluate the function we're trying to solve at the guess. Well, that's right here. It's just 1. The next step is to calculate the slope of the function at the value 1 of the first guess. That turns out to be 1, as can be directly deduced from calculus. And what that says is then the graphical method says draw a tangent line with the slope at the point, and where that tangent line intersects the x-axis is the next guess. That gives us, by simple geometry, the next value of the estimated solution to be 1. And if we wanted to use these numbers, we just plug in the formula and we get the same answer. So the formula is very simple. But that's not good enough. We want to iterate this. So we repeat the process, evaluating the function. At the next guess, it's -1. The slope here is -4, negative. And that says, draw a tangent line, and where that intersects the axis, that's our next guess. Hey, we're getting better. Things may work out. If we can calculate explicitly, that's 3/4, and if we use the formula, we get the same answer. Doing it one more time, I'll skip the details. You'll see that the next iteration gets us very, very close. To my myopic eyes, we're pretty much there. In terms of the formula, this is the value at the third iteration, and if we were to continue this ad infinitum, we would find the exact answer, for which this is a 5 or 6 digit approximation. So already, the key thing here is after the third iteration, we are within 1% of the correct answer. And in fact, that illustrates one of the attractive properties of this algorithm, and that is near the solution, there's rapid convergence, or quadratic convergence typically. For the experts in the audience and for exercise for the students, you might think, well, are there some functions for which this algorithm doesn't converge? And unfortunately, that happens too, but we're not going to go into anything more complicated. But this is the basis for most of the solution algorithm. And with that, we'll hand it back to Radek.
Okay, thank you, David. So we have to walk through a few basics now. The equations that we need to formulate to solve for what is of interest to the designer come basically from 3 different sources. David already mentioned that. The first is Kirchhoff's current law, the second is Kirchhoff's voltage law, and the third type of equations are the individual components and their properties. They are formulated as separate equations. So we have the 3 types. The first 2 types are very easy, very nice, algebraic, simple equations. They have to hold, though, at every single time point, or if we are in the frequency domain, we'll be talking about that later, they have to hold at every frequency. The component equations can be linear, but that's not the case. The case is they're usually nonlinear. They can be differential or integral. So that's where the complication or the issues come to be solved. So for the Kirchhoff's current law, we have a circuit node somewhere, and the node is a point that 2 or more components are connected together. And at that node, the sum of all the incoming currents has to be equal to the sum of the outgoing currents. The currents have polarity, so that's why we have plus and minus over there. In a circuit that has n nodes, there is n minus 1 such equations that are independent. So usually there is one node that is selected as the reference node, usually denoted with 0, and the remaining nodes are used to formulate the equations. If we go to Kirchhoff's voltage law, it's also fairly simple. For every loop of nodes, closed loop of the nodes, whether there is a component in there or not, really doesn't matter. The algebraic sum of all the voltages are also have to be 0. And again, voltages have polarities, so that's why we have plus and minus signs over there. If a circuit has n nodes and b branches, then the number of independent equations is b minus n plus 1. And it's a little bit more difficult to know which ones are independent. However, there are established way to handle that in a proper way. And we'll not be talking about that, but we need that number of equations. So for the components, these are examples of a few components that can be there. A resistor, an inductor, a capacitor, a field effect transistor, and there are many more. And the problem is to talk about is basically what type of equations are coming from those components. For resistor, we have algebraic equations. The equation can be linear, so linear relationship between the current and the voltage. Or it can be a nonlinear relationship. So the voltage expresses a function, nonlinear function of the current, or current, nonlinear function of voltage, or can be an implicit function. For inductor and capacitor, these are the linear relationships. For nonlinear, basically the magnetic flux is a nonlinear function of the current, and the voltage is the derivative of the magnetic flux. For a capacitor charge, a nonlinear function of voltage, and the current is the derivative of the charge. Transistors are modeled with many components, and those models actually can be fairly complex. From, let's say, simple models that may have 5, 10 branches to many more, and some of the transistors may have, let's say, 10 to 15 parameters to describe, and some may have actually hundreds parameters that describe the behavior. So that's the components that come to the equations. Now, how is that information presented to the computer and to the software or to the simulator in particular? Well, the typical way is the schematic window, and in that schematic window, the user or designer grabs symbols as components from various palettes and puts them on the schematic, makes the connections, etc. And for each component, the parameters of each component can be defined through a dialog like this one. It can be a layout window, and in the layout window, that was closer to the actual implementation of certain components. The user will draw, let's say, like what we have here. It's not, it's a little bit too bright, so we don't see the contrast well. But anyway, these are the traces of metallization on a dielectric layer. And this is a microstrip filter, so there is another metallization layer at the bottom of the dielectric layer. So this is either user-drawn geometry, can be generated from schematics, can go to the schematics, and there's a synchronization between those two ways. Traditionally, though, the computers, the simulators, get the data in the form of a netlist. And that netlist is an ASCII file, like this one, where the individual components are described, the connection nodes are given, the parameters are specified, etc. That's extremely tedious to write it and in an editor, but this is done automatically directly from the schematic window. This is generated and supplied to the simulator. So now let's go to the information that we'll talk about different types of analysis and DC, transient, AC, harmonic balance. And for DC simulation, we have the KCL equations formulated using, let's say, an incident matrix, and I is the vector of the currents. The KVL equations are formulated using, maybe one way of doing that is using some additional unknowns, which are so-called node voltages. And then we have the component equations. So we put them all together. We have the several equations with several unknowns to solve, and that is solved by the Newton method, with the J being the Jacobian matrix that contains all the derivatives. So a simple DC simulation setup can be like this one, that we take a source, we take a component, we take another source, we connect all of them together, we have a probing component that will calculate the current for us, and we define two variables. The user can define two variables, user names chosen, however the user likes, and then this particular setup has two nested sweep loops. The outer sweep loop is facilitated by this parameter sweep controller. So VG is outer, and for every single value of VG that is going to be swept, there is a sweep of VD, this voltage on this source, right on the DC controller. And so, and the probe is to monitor the drain current. So, as a result, we will get the DC characteristics of this particular device. Now, DC simulation is really indispensable for every single other simulation. For transient, for harmonic balance, for in all the other simulations, DC simulation is a sort of first step, whether the user requests that or not. So let's go to the transient simulation now and describe how the transient simulation works. Well, let's start with a simple example. We have a capacitor, and we will charge that capacitor from a source. We connect the source capacitor to a resistor, and that results, well, let's say at t equal to 0, that results in a very simple linear equation, since R and C are constant values, linear differential equation, the known exponential function is the solution, and we can calculate that subject to the given initial condition. Now, to solve the equations for transient simulation, we discretize the time domain. So what happens, we take the first time instance to be considered is 0, then we have t0, t1, t2, t3, and so forth. A sequence of let's say they are equally spaced, so the time stamp is an h. And let's look what happens to a capacitor, what we do. This is a very simple, probably simplistic way to explain that, but it's very basic. So we basically take the capacitor equation. The current is C times derivative of voltage with respect to time, and make the finite difference approximation to that differentiation. So this can be expressed this way, or can be expressed this way, one of two equivalent ways. And if we do that, we need to solve for those n+1 quantities. So in other words, we have the equations of this nature, that I is C over H multiplied by V minus a constant. So this can be represented as a current source in parallel with a resistor, because this is you see that's like a resistor relationship, just a value I to V is proportional, right? Or in the other form, we can say that the voltage is this resistor I times I plus a source. So for the second one, for this one, this is the nice interpretation of what is happening. We basically have a source for solving the source, which is the charge at time Tn. And only the difference will be calculated during the time step. So we solve the equations. It's basically that replace the capacitor at that time point, and we solve solve the corresponding system of equations. And that system of equations, we really have all the sources that are evaluated at the time point are single valued. That's the value at the time point. Original resistors are resistors, remain resistors. Capacitor inductors represented by resistors and sources, and those sources are single value. It's identical to DC setups. So we basically get equations identical as DC equations, and we solve them. That's what we do. And then we use the solution for discretization at the next time point. This is a little bit simplified. That's one of the simplest integration algorithms. Is probably not used anymore much, but should give you the gist of the approach. So transient simulation in action at time 0. This rectangular waveform is launched, and at the input as a stimulus, and then the resulting waveform is shown like this one. It can clearly be seen that the response is not periodic. In other words, does not repeat identically. That's the time of transient effects that they have to. It takes some time to run the simulation or for the actual device to settle. So the transient will disappear after a while, but if we are interested in looking into the solution after it settles properly, that's not necessarily the best approach to do it. And we'll be talking about that a little bit later. So I think we'll switch at this time point.
So the next analysis mode we'll consider is AC. And we'll go back to our simple circuit, but we'll add two small levels of complexity. The first is we'll add a capacitor to the circuit. And the second is we'll add a small sinusoidally varying, time-varying source to the DC. So if we look at the total applied voltage versus time, we have the DC that we had before at 1 volt in the red, and a small 0.1 volt peak-to-peak sinusoidal excitation on top of the DC. That gives us the time dependence. And the assumption of AC analysis is that the time variation is small in magnitude and is sinusoidal. And under those two assumptions, we can linearize the circuit, which is a theme by now you can recognize for nonlinear solutions. And for small perturbations, this time-varying nonlinear circuit can be represented exactly as the original DC circuit. In fact, as Radek indicated, that's the circuit that's solved first, even when you request an AC analysis. First, the DC is solved. That gives you the main component of the current through the diode. And then there's an independent linear circuit where the source is the small sinusoidally varying voltage, and the elements of the linear circuit are constant. And in particular, since this resistance came from the nonlinear component equation, it's actually calculated by linearizing the nonlinear expression that we had before for the diode current at the DC solution. And all those derivatives were found previously in the process of solving the DC. I won't go into the math further, but that's the concept. Now, one of the attractive aspects of linear and small signal circuits is that they can be easily analyzed in the frequency domain. So Radek introduced the major component equations in the time domain, where they're time derivatives, but in the frequency domain, we can exchange time derivatives for multiplication at the cost of introducing exponential notation. And I'll assume this is familiar. And that simply saves algebra. So if we had a sine wave here, the voltage would be cosine and vice versa. But the amplitude and the phase, the two parameters associated with sinusoidal signals, can be represented by a single complex number because it has a magnitude and a phase. Now, therefore, in the frequency domain, with the V's and the I's complex, a magnitude and a phase, the component descriptions now become remarkably similar and, in fact, can be subsumed in a simple linear complex now relationship. So it's simple but complex, not complicated. Z is a complex number known as the impedance, and this gives us a linear relationship like Ohm's law in the frequency domain. And because this circuit is linear, we can do a lot of very simple calculations using the simple laws of series and parallel impedances now, as if they were real resistances. So a lot of this you can do in your head, and you can check that this is right. Now, if you're looking at the entire circuit, and not just del V, which is what this result is, we can represent it as an impedance. It's a complex, nonlinear function of frequency, complex value, and it gives the response of the circuit as a function of frequency. And that's why people are interested in this kind of analysis. You apply it to a circuit or a transistor, you sweep the frequency, and you see the sensitivity of your circuit to frequency. So AC in action, we will apply to this circuit at the DC operating point, and we'll take a nanofarad capacitance, fixed in value, and we'll sweep this source from basically DC out to 10 gigahertz. That's 10 to the 10th cycles per second. And if we look at the magnitude of the voltage here at this node, at very low frequencies, it's a half, and that's because there's no current through the capacitor, and so the voltage across the whole circuit is divided evenly between the resistors. But at high frequencies, the current goes through the capacitor, and therefore this node approaches ground, so it becomes zero. And if we look at the phase, we can interpret that too. At DC, all the current is going through the resistor here. Everything is in phase with the voltage, so the phase is zero. Whereas at high frequencies, given our complex algebra that we looked at before, the current becomes going through the capacitor completely, and therefore it's out of phase by 90 degrees with respect to the stimulus. What's often done is, because this is complex, is to plot this on a polar chart. So this is the combination, the magnitude and the phase, starting here at a half on the real axis, and as the frequency increases to 10 gigahertz, we follow this trajectory, and all that information can be contained on a single plot. People in microwaves use Smith charts, but we're not going to go into that here.
Okay, thank you. So the next little segment is on harmonic balance simulation technique. And out of the three types of simulations that we have already discussed, DC, transient, and AC, two were steady state, AC and DC. Transient is transient that can settle after a long time, perhaps to show the steady state. What is the steady state in general? We will talk about that later. For DC is DC stimulus, DC response, from minus infinity to plus infinity, or number to number, that's all. For AC, sinusoidal excitation, response is a sinusoidal excitation response of exactly the same frequency. And for harmonic balance, it's a little bit more complex, and it's very interesting. So what we have here is a simple example that we have a sinusoidal source. We have a resistor, capacitor, and a diode. And this time we actually have a real diode. For this, we use a sinusoidal excitation, and we get a distorted response that is not sinusoidal. So how to represent that distorted signal? Well, we can decompose it to sinusoidal parts or sinusoidal signals with different frequencies. Basically, we go to the frequency domain, and it is shown that this particular waveform can be shown as a sum of those three. Actually, we have more than that we use, but the others are so small that will not be sort of visible in any good way with this scale. But anyway, we have two periods of the fundamental sinusoid. We have 4 periods of the second harmonic, and we have to blow out this part to see the third harmonic, and there are 6 periods over here. And in this frequency domain, or corresponding to the frequencies of those decomposed signals, we can get the magnitudes and the phases of the corresponding terms and plot them in this fashion. So the frequency domain, we use the Fourier series representation of those periodic curves, and we are trying to solve the steady state, which basically can be summarized briefly as if we have periodic excitations, we get periodic responses. So DFT could be used to do the Fourier series representation. It is actually used probably exclusively FFT for that purpose. Well, the practicality of the harmonic balance methodology comes from the fact that we can truncate. I didn't show the 4th and 5th harmonic because they were small enough. And it may be the case that, well, we may have to go to many more than 5. For certain purposes, but in general, we can stop somewhere. We don't need the infinite expansion. And how the equations are formulated is shown briefly here. That Vn represents the nodal voltages in the frequency domain, so there are basically phasors at each frequency. And they are first transformed to the time domain. F is the FFT operator. Then the actual time domain representation is applied here. Then we get the time domain response of individual components that are translated back to the frequency domain using FFT. So this part will correspond to nonlinear resistors like the diode over there. This part will correspond to the capacitor, nonlinear capacitor. You may see actually this very interesting symbol here. That's basically what David already showed, that multiplication by j omega corresponds to the differentiation in the time domain. So in the frequency domain, we get algebraic operation instead of differentiation. So we get algebraic equations here, and some other linear components may contribute to this part, and the excitations may be here. So the equations are solved. I formulated, and the equations are solved again using Newton method. So a simple example, we have a simple circuit here, a source, another source at a different frequency. This is another frequency, RF frequency, LO frequency. That's a mixer, one amplifier, another amplifier, a couple of filters. And actually this is a sub-circuit, so the design is hierarchical. We can get into that, and that the mixer is shown here. Like the one that before was shown on one of the previous slides. And we run harmonic balance simulation. This is run with a two-tone case. and we get the responses at this point is the IF frequency response and a whole bunch of other spectral components. Designers may be looking specifically for the levels of those spurious spectral components. Some are unwanted more than others, etc. So that's where the designer what the designer is going to look for and make decisions, trying to modify the design, etc. Now, just one slide on the results in general. The results, the plotting is very important. That's the presentation of the results for the user. We have already seen several plots, but numerical data can be also outputted. Furthermore, actually, the user can define equations, some expressions, and this is an expression that calculates the power dissipated in the diode. That can be shown as well. So all of that is easily available to the user. So we have the last segment, and David will take over and talk about test parameters and XParameters.
Thank you. So let's go back to when we talked about AC analysis. It's a linearization around the DC operating point. And at very high frequencies, we're going to re-express that in terms of so-called power wave variables. So it's still a linear analysis. It's still in the frequency domain. But we're going to take linear combinations of voltage and current to define new dependent and independent variables. The interpretation of these linear transformations is that they more closely correspond to the notion of propagating electromagnetic waves and the reflection of those waves or the transmission of those waves through or from a component. There is no more information contained in this description than in standard linear theory in terms of impedances or admittances. It turns out to be just a much more convenient way at very high frequencies, say gigahertz or tens of gigahertz or higher, to make accurate calibrated measurements with modern instruments. And that's because to measure things like Y's or Z's, you need boundary conditions like shorts or opens, which are very difficult to enforce at those frequencies. So basically, if we make these transformations, and notice the units of A's and B's are the same, you multiply an A and the B, you get units of power, hence power waves. Of course, if you multiply current and voltage together, you get power. So it's the same kind of thing. And Ohm's law, in the frequency domain that we discussed before, in the new variables just is written this way. It's another linear relationship between, in this case, the incident waves, A, and the scattered or transmitted waves, B. But it is linear. And so any component that's typically related with an impedance or an admittance can be represented exactly the same, sometimes we use the squiggles, by giving its S parameter, or if it's a multi-terminal component, its S parameter matrix. There's an explicit formula, since there's an explicit formula for the variable transformation, and if you know the impedance, you can calculate the S parameters. The great utility of S parameters, besides the ability to measure them accurately, is that it's possible to characterize the S parameters through measurements or calculations on the simulator of a component or two components, say component 1 and component 2, measure them in that case, and the algebra is simple, it's linear. And if we have the S parameters of two components, we can cascade them, apply the circuit laws, and predict with absolute certainty the linear performance of any circuit or system built from these components. Great utility, hierarchical and accurate. The question is, we've just been talking also about nonlinear components, and any component, if you drive hard enough, becomes nonlinear. And that's what X parameters are. So X parameters try to generalize the S parameter concept, and the key here is, finally, there is now a rigorous way to do that. So one of the things Radek mentioned is that you can excite a nonlinear component with a sine wave and get waves, get responses that have components at other frequencies besides the initial frequency of excitation. Those are the distortion components. They're usually unwanted, and they change the shape of the curve, as you've seen. So XParameters finally give us a way to rigorously capture that phenomena. And we have a new instrument that we talked about a little bit last time I was here called a nonlinear vector network analyzer that measures not just the S parameters, which are ratios because we have linear system of scattered to incident waves, but actually the absolute magnitude and all the relative phases among the different spectral components of the waves. And that's a new concept at these frequencies. It's a multi-channel instrument. It requires a new type of calibration with a phase reference. It's like a multi-channel scope, and I don't have time, unfortunately, to go into the details. It's very interesting. But there is now finally a way to make these measurements. The model, because we're dealing with nonlinear components, is necessarily more complicated than the linear matrix of S parameters. So now, since we're dealing with multiple ports, say this is the input and the output, we have a port index, like we did before with S parameters. But also because the input at one frequency can have an output at a different frequency, we also have to index these nonlinear maps by, say, in this case, the harmonic index of the response in which we're interested. The other problem is the complexity. This particular output, say the second harmonic at port 2, is a complex or complicated, both, nonlinear function of the biases applied to the amplifier and the magnitudes and, in particular, the phases of the different spectral components incident at each port simultaneously. Because it's not a linear system, we can't appeal to beautiful theorems like superposition to do everything with one signal at a time and just add the results at the end, unfortunately. That's life. But the paradigm is sufficiently powerful that with the X parameters, if we're willing to deal with this complexity, computers are good at that, then we can in fact cascade these nonlinear blocks and take the more complex excitation and their interaction into account with the nonlinear simulator. And thanks to Radek, we actually have a component in our ADS simulator that will allow you to take the measured X parameters or the calculated X parameters from your schematic and put them into components. Conceptually, what we're saying now is you take a nonlinear block, in this case an embedded mixer and an amplifier, including the bias dependence, and you excite it at as many terminals as it has with its incident waves. Now remember, the incident waves in blue at each of these, say, 3 RF ports have fundamental, second, third, etc., harmonic components. And you measure the responses at each of the ports and the DC. There's also RF to DC conversion in these devices. So the system synchronizes all those measurements for you. And then the nonlinear block is characterized at each port by a set of nonlinear, complex valued maps from the incident signals and the DC voltages, wherever they are, to the outputs. Complicated, but straightforward in principle. Now, how do we simulate that in the circuit simulator? Interestingly, we can consider these X parameter blocks together and we attach them at a common node. The circuit laws, which we started this discussion with, are very intuitively expressed in wave space. So in particular, at this internal node, this incident wave has to equal the scattered wave from the component that it's connected to, and vice versa. Whatever the scattered wave that comes out of this component at the solution of the circuit is identical with the incident wave here. And these two equations are none other than our famous circuit laws that we originally discussed in voltage and current space. Then the simulator eliminates the internal variables by a set of nonlinear equations, and it uses, what else? Newton's method. So that's how it works conceptually. Now, one of the great advantages of this approach is that unlike, as Radek showed you, harmonic balance using time domain models, which is the canonical way of characterizing a nonlinear component, a transistor typically, there's no need to go back and forth. If you have your nonlinear component described already in the frequency domain, there's no FFT. You don't have to go back from the solution of the circuit equations and frequency to look at the waveform that your time domain defined model gives you. You've already modeled it in the frequency domain, so you save the back and forth. Also, if you don't have a model, as some of the newer components don't when they first come out but are still useful, you can measure your component and describe it as long as you sample it densely enough and you're willing to stimulate it richly enough. You can just measure it and suck it into a block as if it were an S-parameter block used in simulators as they have for years. So X parameters in action, we're going to apply X parameters to a FET. This is a MOSFET, but we're actually going to show you results for gallium arsenide FETs and more recently gallium nitride devices. Now if we were to apply the complete general theory to every device, that would be overkill. There are many dimensions, these are each complex numbers. We'd have a long time consuming and complicated set of measurements. So we're going to again invoke, for simplicity, not for necessity, the idea of linearization. So we're going to linearize now this generic set of nonlinear maps, not around the DC operating point as we did for AC or S parameters, but we're going to maintain two full independent large signal components, namely the strong drive on the transistor and, in this case, a strong reflection. This would correspond to matching the transistor to deliver power most efficiently, or sometimes it's called load pull. And we do this with two independent sources, so we drive the device with incident waves at the same frequency, and therefore we have to keep track of the relative phase, unlike S parameters. But we can treat all the harmonic dependencies linearly. That's what we do for convenience. And S parameters when we treat every component, every RF component linearly. So this reduces exactly to your standard S parameters. But taking only two nonlinear components into account, we can predict, say, the voltage waveform in time under large signal stimulus. It's a little bit distorted. The simulations here are in red. The measurements are the blue circles. They're almost on top of each other. And the current, which is the green symbols measured and the X parameter simulations in blue under highly distorted conditions, extremely well for this device. No standard model can typically do that well. And here is a higher power device in a popular 3.5 semiconductor called gallium nitride. People are working hard on models, but the devices are useful and people need to simulate circuits. So you measure the device and you can get this kind of model accuracy for the current waveform and the voltage waveform. Voltage here and current here. Measurements in this case in red and simulations in blue. Just to let you know, these terms are analogous to the S parameters. They're proportional to the incident waves. X parameters require a new set of terms that are also independently proportional to the conjugate of the same phasor. That's related to mixer theory. Because you have multiple signals, you get image frequencies of plus and minus the combination. So there's lots of interesting things. The neglect of these terms is what has led people to down the wrong paths trying to generalize the linear S parameter theory to the nonlinear X parameter, or the nonlinear case consistently. That's been a dead end. So I think that brings us to the conclusion section. So I hope we've convinced you that circuit simulation is really indispensable for the design and optimization. Unfortunately, we didn't have time to talk about optimization of electronic circuits and systems. That is due to the complexity of the circuits, the nonlinearity of the components, the complexity of the signals, etc. You couldn't possibly do all this in your head or with graphical techniques, but you have a computer, hence computer-aided design. We've only had time to scratch the surface of a few basics of analog circuit simulation. As Radek said, there's digital, and there's each of these topics you can go into in much, much more detail. So we've covered in particular very briefly just the standard analysis types and spent a little time on one that we hope will become standard over time. As usual with technology, as technology evolves, there are new types of circuits, systems, technology, and they will continuously drive advances in this very interesting and highly interdisciplinary field of circuit simulation. So thank you all very much for your attendance, your interest, and we'll be happy to stay for a long time and do our best to answer your questions if we can. Thanks.
Thank you very much.